Hey there, and welcome to this last lesson on higher mathematics geometry. So for this final lesson, we're just looking at two related but different topics, loci and vectors, two sort of smaller topics that tend to be asked in some of the more advanced questions that we need to make sure that you're familiar with. So let's take a look at what we'll be doing. So loci around a point. So first of all, I've mentioned about loci, locus a few times before throughout geometry. So we're going to look in more detail what that is now. What is a loci, say, around a point, loci around a line? So just a little bit on loci, and then the main thing we're going to be looking at today is vectors. We're going to look at what a vector is, how can we use them, how do we do arithmetic with them, and then how can we prove things using vectors. These tend to be some of the real sort of top rate questions like vector proofs. They can get quite tricky. So let's take a look at that. So first of all, loci around a point. Um, so a locus. So first of all, I find a lot of the problems that people can sometimes have with this is not knowing what that word locus even means. Like you might have a question that says draw a locus of whatever, and if you don't know what locus means, obviously that's going to be a problem. So let's get that definition down clear. So locus is like the set of all points that will meet some particular algebraic or geometric condition. So we could take something like this, say with point A, and say if we want all the points that are some distance away from A. So we've kind of seen this before. So we're talking some distance from A, but in any direction. And you can see what that's going to essentially map out. It's a circle. That's essentially what a circle is. It's the locus of all points that are some constant distance away from another point, which would then be the center. We've also seen with, say, bearings. If we have a point B here and we draw a north line, and say if we have this particular bearing angle and we want the locus of all points that are on that bearing, it's going to be essentially this line. And if we then wanted to know, okay, what is the set of all points that are on both of these loci, then it would just simply be the intersection. So it's kind of applying a lot of the principles we've already learned about, circles, bearings, intersections. Um, but it's just a different kind of wording that can be useful in certain situations. So here, this locus, the points that fit on both loci, you see reduces down to just simply 2 points, as opposed to a circle, which is essentially like infinite number of points around that circle. Um, so if we take, say, this, we have 2 points A, B, and we draw a locus with a constant radius, so it's going to be two circles around A and B, the intersection of those 2 points here, and say if we have the line between A and B, that line um, between the intersection of their two loci, it doesn't matter what the radius of those circles are, really, as long as they intersect. That we get those two intersection points and then draw the line going through it. That line will represent what's known as the bisector of the distance AB. So it cuts that line into two equal pieces. So we saw this last time, like with circle theorems and a tangent line and a chord, uh, if it intersects at a right angle, it um, cuts the line into two pieces. It's kind of a similar thing here. This is going to be right angle, and it will cut AB into two equal pieces. Um, and also, the points along that perpendicular bisector, every point is going to be equal distance from both A and B. So you see this point here, that essentially forms an isosceles triangle, and those green points you can imagine sliding them up or down, that distance from to A and B is always going to be the same because it's always going to be an isosceles triangle. And so those points along those lines are going to be said to be equidistant to points A and B. Equidistance meaning it's equal distance to both of those points. So now let's look at loci around a line, which is similar but a little bit different, a little bit more complicated. But now that we've got a kind of good understanding of what a loci is, what a locus is, we can do that around, say, a line. So say if we've got 2 points A and B and we've got the line between it, and we want the locus of all points that are some distance away from this line, maybe this distance here. And first of all, let's consider like the maximum possible distance we could be. So like let's say like this, where we've got the line basically perpendicular to our line AB. And you imagine sort of sweeping this around like this. It's going to kind of kind of like the same thing we did around just a particular point, but it's also just going around this whole line now. You can see at each point, it's going to produce a circle, but along the straight parts, it's going to produce, just a straight line like that. And so this would then be, the maximum sort of distance we could be away from this line, based on that distance we had. But also, we could also be anywhere within this line. Like say if we, changed the the direction that distance was going in, you could point to any point in this line as well. Uh, for this, where the two circles at each point don't intersect, if they do intersect, then it would become a little bit more complicated. But generally, you don't really encounter those kind of scenarios. But if you just think about it, you just got to think, like draw circles around each point, draw lines along here, and think, okay, what kind of regions could it, you potentially point to with a distance that long, and what ones could you not? Um, so that's loci around a line. Another thing we might do is say if we've got two lines meeting together at an angle and we want to bisect that angle, like the same way how we cut a line into two equal pieces, that's what it means to bisect. Here we want to bisect the angle and cut that into two equal pieces. A thing we can do here is that point where the two lines meet, if we draw a circle around that, so I'm just drawing part of the circle here, because all we need is basically those intersection points with this line. And then we draw another circle around of the same radius around those 2 points, um, and find where they intersect, which is here. Finally, we can draw the line through our starting point and that new point we've created, and that will bisect the angle. And the reason for that is because think about it, like we drew a series of circles there, which are the same radius. So you see that the distances from the center points of those circles to the edge of the circles are going to be the same, and so that essentially forms a isosceles triangle here. So those two angles are going to be the same, but also we're going to get the same isosceles triangle over here. It's kind of symmetric. So you see that angle that we started off with has now been split into two angles that are going to be equal because these two triangles are congruent. They're the same triangle. But you don't really need to be able to prove that. You can see that it is going to be that, but you don't have to prove it. You just need to know how to bisect an angle. Right. So that's it. It's only a little bit on loci. It's just a matter of knowing what it means, and then a lot of it we can kind of work out quite logically, or using a few techniques like we saw there, bisecting a line, bisecting an angle. Now let's look at vectors. So we touched on vectors briefly with when it came to translations, but in general, a vector is just some magnitude in a particular direction. So the word magnitude refers to some arbitrary quantity. So it could represent anything. That's what makes vectors so powerful. Like they can be used to represent all sorts of things. But, at GCSE level, we're just going to consider it as like a distance in a particular direction, which is certainly when you're first learning vectors, the best way to sort of understand what's going on. And even in a more abstract circumstances, it's normally the way we would visualize it. So say if we had an axis like this, and we plot a point here, and we have a particular distance. So this isn't like the loci, like where we had a distance, but in any direction. So it kind of maps out like a circle, circular locus of points. We're talking about a distance in a particular direction. And so it specifically points from this point to this point. And we would define that vector as 9, 5, like we saw when we was translating a shape, because it's moving 9 across to the right and then 5 up. And so we represent that by this little column vector of 9, 5. And an important thing about a vector is that it doesn't matter where it starts from. So say if we had this one here, starting from the point 4, 2, you see here we're also going across 9 and up 5. That's the same vector, 9, 5. So a vector is like a relative quantity. So it's telling you from given a starting point, it tells you where you're going. So you go in, so much across and then so much up or down, as the case may be. So yeah, so these two vectors would be the same, even though they're at different points. So remember what a vector is. We need to really sort of drill that in. A vector is basically just a distance, but a distance in a particular direction. So if we had say -9, -5, that would be the same vector, but like in the opposite direction. We'll see that more in a minute. So sign plays a role here. like distance, we can't have a negative distance, but when we're talking about direction as well, sign does make a difference. So now, let's look at some vector arithmetic. So when we're trying to do arithmetic with vectors, so say addition and subtraction. So let's draw in a bunch of vectors first. So I've got some vectors like here. You might want to pause here and you could have a look and see, that those vectors make sense. You're going 4 across and 12 up for the first one. The next one is 8 across and 3 down. -3 means going in the opposite direction to our usual X and Y direction. So, and 4, 8 is similar. So we can label these essentially A, B, and C, essentially like we have done with variables in algebra. Vectors we label a little bit differently. We either write it in bold or we underline it, or sometimes both. And that distinguishes it from, say, an unknown number, like in a variable or an unknown constant, say, in algebra, because sometimes we might be encountering two at once. And a vector is a fundamentally different thing, isn't it? Like, say, if when we've been dealing with algebra and equations before, you might have x. X is just some unknown number. But here, this is not a number at all. This is a vector, which is a different thing. It's like a list of numbers, a column of numbers where each one represents a different direction. So yeah, that's important. And so okay, say if we're just adding these vectors, what does that mean, and how do we calculate it? So first of all, let's look at calculating it. So we're just basically doing this, adding for the three vectors. How does that work? Well, we can just add across the top and bottom. Because you think about it, I mean, that might sound strange, when you think about fractions, because we know we can't do that. But this is a vector. It's so the top is representing how much we're moving in the x direction. So if we move across 4, and then we move across 8, and then we move across another 4, we're moving across 4 plus 8 plus 4. So we can just work out the net result there. If we, in the y direction, we're going up 12, down 3, and then up another 8. And we can work out the net result there by, just combining those. And so we get 16, 17. And if we draw that on this graph, it looks like this. And okay, like graphically, like what does that mean? Like in terms of these vectors, A, B, and C, what does this net result mean? It's basically as if you put all the vectors together end to end. So you go A, and then you go across B and across C. Because remember, like what I was saying, the vectors, it doesn't matter what the starting point is. It's like a relative quantity. So from a starting point, you go this distance in this direction. And so we can change the starting points, make the starting point of B the end point of A, and make the starting point of C the end point of B. And that would be essentially A plus B plus C. And you see this blue one is then just effectively the net result. So that's what it means to add vectors. It's the net result of all of them. So say if instead we had something like this, A plus B minus C, what would that look like? So first of all, we can calculate it fairly easily. So similarly, we just add and subtract across the top. So this time we're minusing 4 and minusing 8 from the x and y displacement. And we get this end result. And we can draw that on here as 8, 1. Graphically, what that would look like is, okay, we've done A plus B as usual. So we're going A and then we go across B, but then we're going minus C. And what that means is we're going that same distance C, but in the opposite direction. And you can see that gives you the end result of basically 8 to the right and 1 up. So that's what it means. So we're going to look more on that now. So we have a vector, say this one A, and because one is this coordinate system, you could pause here and work out what the actual vector A is in terms of like X and Y motion. But I want you to start thinking about vectors just more in the abstract, because we're going to need that for some of the harder questions. So a vector is basically a distance in some direction. So say here we have this vector A. Imagine the axis isn't even there. It's just a distance in that direction. What does it mean to then say if I triple that vector, I do 3 times A, it would look like this. And if we did, minus a half that vector, it would look like this. And so multiplying a vector has the effect of scaling the vector. And so This is why these numbers, like that 3 and that minus a half, in the context of vectors, are often referred to as scalars because they scale the vectors. They make them longer or shorter, or they can change the direction, but it doesn't change the direction, and that is critical. Like we really need to, understand that the direction is still the same, or at least it's on the same line. It might be going in the opposite direction, but it's along the same line. Um, so if we notice, yeah, that the size of the vector changes, but the direction, as in the line, is preserved. Or certainly, if we say one like this, where it's 3/2, so we've done half of that vector 3a, and we're doing it from a different point now. So okay, if they're both kind of going from the same point, with like the minus half a and 3a, we can see it's going to be along the same line. If it's not, because it's still going in the same direction, what we're going to get is essentially a parallel vector. Like you see 3/2a and 3a, they're parallel lines. So uh, that's important. If you've got one vector as simply a multiple of the other, it means that they're either on the same line or they're parallel to one another, depending on where they're starting from. So that's a really important result that we need to know. It's certainly for some of the harder vector proof questions, which we'll see soon enough. Um, so yeah, if they're scalar multiples of one another, it means they're either parallel or anti-parallel. So anti-parallel means, so we have parallel, like with parallel lines means that they're both going in the same direction, but like they're the same kind of angular direction they're going in. But vectors have like like just a regular line like we sketch. It's kind of, we're always just reading left to right, whereas a vector can go right to left, can't it? And so anti-parallel means that they're parallel, but they're going in opposite directions. So you'd see 3/2a here is parallel to 3a, but it's anti-parallel to minus a half a, because minus a half a is parallel, but it's going in the opposite direction. So um, just in case you come across that word anti-parallel, that's what that means. So let's look at some actual problems with vectors now. So a simple one here is, where we have a triangle and we're putting these side lengths as vectors. So A and B are like different directions, and we've represented AC and BC as vectors. So it's a distance in a particular direction. And we've got this point P, and the point P is on the line AB, such that AP to PB are in the ratio 1:2. So vector questions, they love to like put in little ratio problems with these vector problems. But they're normally pretty straightforward. So the simple thing here, say if we wanted to find out what the vector A to B is, because we don't know what that is here, we can use our understanding of vectors and vector arithmetic to find out what that's going to be. Like A to B would be the same thing as going from A to C and then C to B. And what that's going to be is the same thing as A to C minus B to C. So you see there, CB is the same thing as minus BC because it's the opposite direction. And we need to use that here because that's something you've got to be really, really wary of here. When we've got these vectors, they're not just distances, they're distances with a direction. So 2a is specifically the vector from A to C. C to A is going to be minus 2a. And same thing on the BC line. We've got B to C is the vector 5b. C to B is going to be minus 5b. So if we want the vector A to B, we're going from A to C, which is 2a, and then C to B, which is minus 5b. And so we get the result 2a minus 5b for the vector AB. Now, using that ratio, we can see that A to P is going to be 1/3 of the distance A to B. Because we've been told A to P and P to B are split in the ratio 1:2. So using that basic, understanding of ratio, we can see that that distance A to P is 1/3. It's one out of a total of three parts. So we've got AP is equal to a third of AB. So therefore it's 1/3 of, 2A minus 5B. So we can just work that out like that. So that's a simple example of using vector arithmetic to calculate a problem like that. We wanted to get the vector from A to P. So, okay, let's take a slightly more complicated scenario. So I want to make a comment quick on the, where we always tend to get things in terms of like say A and B or two unknown vectors. You'll notice this a lot in problems. So A is set in one particular direction, B is set in another direction, and then we put everything in terms of those vectors. And the reason we use that for is it's all to do with creating like an arbitrary coordinate system. Like where we have normally just perpendicular coordinate systems where x is going left to right and y is going up and down. We can also create a coordinate system, say like this, where you can see A is like going in the y direction, but it's not vertical. It's like on a slant, and X is going in the B direction because you see 3B is going horizontally, so therefore B is going horizontally, and you see A is going up in that like in that slanted way, and so we know A is going that way, and so that's why we tend to put things in A and B. It's like we're putting we're like it's like we're doing coordinates, but like in this slanted system where so if we was reading x and y coordinates in this system, it would be like x would be reading left to right, but then y would be going up like diagonally. And there's reasons why we would sometimes do that, but they're a bit beyond, quite far beyond GCSE level. That's more like undergraduate level mathematics. But I just thought I'd say that there, just so you can understand why it's always in terms of like A and B like that. And any problem you get, you want to try and deduce where that A and B direction is going if you can. Sometimes if all the vectors you've been given are in terms of A and B, then it might, it's hard to separate out which one's which. But here, because we can see AD is A, so we know A is that direction and B is specifically horizontal because 3B is going that way, so therefore B is also going that way. We now know what the directions of A and B are, which you'll see in later problems will be really important. So I just thought I'd mention that there. When the okay, so now we're looking at when the line BC is extended, it intersects EF with the point X, and we want to find the ratio of where it splits EF from E to X and then X to F. And we need to use the fact that the sides A, B, D, C, and EF, those horizontal lines are split in the ratio 3 to 2 to 1. 3 to 2 to 2, sorry. Okay, so this is what we're doing. We're extending that line BC, and we want to find when it hits at X. So first of all, we know E to F and D to C are going to be 2B because we see those horizontal lines have been split 3 to 2 to 2. So AB represents three parts. So therefore one part is going to be B. What AB represents is 3B, isn't it? And it represents three parts. So one part is B. So therefore the two parts that make up DC and EF are going to be 2B. So some basic ratio we need to use there. Now BC well, let's back up a sec. So, what are we actually trying to do here? So, really, what we want to do is try and find where x is along EF. So, if we can find out, say, what CX is, that would allow us to work out what, say, EX is, and we could compare that to XF, and then we'll see what the ratio is. So, how are we going to find out what CX is? Well, we're told that CX is an extension of, BC. So they're going in the same direction. So straight away, that should be telling us, CX must just be a multiple of BC. And we can use that. So, okay, let's find out what BC is because we can do that. BC would be the same thing as B to A to D to C, going round that bottom shape. So, okay, so we've got minus 3B because we're going the opposite of A to B. We're going B to A. Then we get plus A and plus 2B. And we can bring that together. Like you always want to bring it together in terms of our, two arbitrary vectors we've got, like A and B. And so we can see that is BC. Now, we need to use again, just like with circle theorems, we don't want to lose sight of just our general understanding of geometry and shapes and things. Like we know that these two angles are going to be the same because these horizontal lines are parallel and we've got AD and A and DE are like the same distance in the same, or most importantly, they're going in the same direction. So they're going to cut those parallel lines in the same angle. Remember what was doing on parallel lines before. Likewise, these two angles will be the same because they're going in the same direction because we was told, that it's an extension. CX is an extension, so they're going in the same direction. So we know those angles are the same. So we can use that to, like how you see that ADDE are both equal. It's A and A. Similarly, you're going to get B to C and C to X are going to be equal. So it's A minus B. So using just a basic understanding of geometry there, using the fact that vectors are not just distances, they're distances with a direction. So we can often infer some angles like this. Um, Now, this gives us the ability to work out what EX is, because we can go E to D to C to X, which are all known vectors. So we're going minus A to B and then A minus B. So I haven't put an arrow on that, but A minus B is going from C to X. So add all that up, collect together the like terms, and you find out it just comes out to B. Therefore, EX and XF are in the ratio 1 to 1. They're basically equal because you see EF is 2B, and we've shown that EX is B, so therefore XF must also be B. And there we go. So that's how we would solve a problem like that. So let's take a similar problem like this, where yeah, this one can be a little bit tricky. It really, requires us to understand the vectors well. So say if we've got a point A on XY such that XA and A to Y are in the ratio 4 to 1. So straight away, that tells us basically that X to A is 4/5 of the way to Y, because it's 4 out of a total of 5 paths. Point B is on YZ, is such that Y to B um, and B to Z are in the ratio 1 to 2. So okay, let's start putting this information in. Oh no, sorry, we've got one more piece of information. Given that the points A, B, C are collinear, find the vector ZC. Right, okay, so let's put in this information. So first of all, we've got the point A here that was told on a ratio 4 to 1. So let's split it up like this, 4A going from X to A, and then one lot of A going from A to Y. Now the point B goes here. And what we're told is that A, B, C are collinear. So that's another key word you need to be familiar with. Collinear, meaning they lie on one linear line, which is a straight line. So YZ, let's try and calculate what that is. Because we need to know what YB is. But we can't really work out YB directly. But if we can work out YZ, we can then use that ratio that was given to find out what YB is going to be. And YZ we can work out because we can go from Y to X and then to Z. So Y to X is minus 5A because we're going in the opposite direction to our vector there, like that was 5A. And then we're going positive 2B. So we get that vector for YZ. So therefore YB, which is 1/3 of the way using that ratio, 1 to 2, is 1 out of a total of 3 parts. So Y to B is going to be 1/3 of that vector from Y to Z. Again, be mindful of directions. Y to Z, and we're going 1/3 of that now, so it's Y to B. Always got to be mindful of the directions things are going in. So we've got Y to B is this. Now, say if we try and find A to B, and then we could compare that to say perhaps BC or AC, because we know we're told that they're collinear, A, B, and C. So that means AB and BC or AC, they're all going to be scalar multiples of one another. So we need to use that information somehow. As always, questions, you'll never be given just redundant information. You must be using it in some way. So AB we can work out by going from A to Y, which is A, like little a, and then Y to B, which we've just worked out, which is 1/3 of this other vector. Whenever you get something like this, you always want to expand it out, collect together your like terms, maybe even factor out a common scalar, which in this case we get minus 2/3. So A to B is this. And so therefore, because A to B is just some scalar multiple of A minus B, A to C must also be just some scalar multiple of A minus B because they're on the same line, like what we saw earlier with scaling vectors. So Z to C, we could now get an equation for that in terms of K. So, okay, we're going a bit around the houses here. So rather than going from Z to C, we're going from Z to X, which is minus 2B, then from X to A, which is plus 4A, and then finally from AA to C, which we've got in terms of this K, K lots of A minus B. So that's what we're doing there. So this is kind of the way you've got to sort of think of things. It's like path finding, like looking through a map, and you're trying to find a path. So you want to get from Z to C. Okay, let's try and find a path through that will get us there. And we can just combine all the vectors together. Now, again, we want to collect together like terms, but you see the coefficients of those are going to be in terms of k. Now, what do we do with this? This is then the really, often could be the really tricky step. And that's why I was talking about earlier in terms of understanding what directions A and B are going in. So you see here, X and Y is, say X to Y is, 5A. So we know A is going in that general direction, that slanted direction. X to Z is 2B. So B is going in that horizontal direction. Now notice Z to Z is also going in the horizontal direction. It's not slanted at all. It's just horizontal. That tells us that Z to C is just going to be some multiple of B. There's not going to be any dependence on A here. It's just going to be a multiple of B. And so that tells us that 4 plus K, that coefficient of the A, must be 0. And so that tells us that K is equal to minus 4. We can substitute that back in so okay, the coefficient of B is going to be minus 2 minus 4. 2 minus 4 is minus 2. Minus 2 is going to be 2. So we find out it's just going to be 2B. And so you see that there's that little step, that understanding of the vectors and how they work that's required to solve that. Because otherwise you'll get bogged down in these answers that where you've got these unknown constants and you don't know how to work it out. That's what you want to do. You want to look at what is the vector dependent on. Is it partly A and partly B, or is it just A, or just a scale factor of B? And we can use that to help determine what that unknown K is going to be. Right, so now let's look at some vector proofs. So this is like where before we were trying to calculate things. Vector proofs is more like when you're trying to prove something. So like say with this example here, we've got point A on MP such that M to A and A to P are in the ratio 2 to 1. So we can see, okay, 2/3 of the way along MP is where our A is going to be. Point B is the midpoint of OP. Given the MNPO, so this whole shape, this whole quadrilateral is a parallelogram, show that N A B is a straight line. So okay, let's draw in our points first. So A is 2/3 of the way along from M to P. B is in the midpoint of OP. And what we're trying to show is that this line here is a straight line, that there's no like kink at A. It's just purely a straight line. And we know what we need to do then. So we need to show that NA and AB or NB are scalar multiples of one another. That's the end result. That's what we need to do. So that will prove this answer, this result. So how we need to do that. So we need to try and come up with some expression for these vectors. So first of all, we know that N to P and O to P are going to be 2B and 2A respectively, because the other sides of the parallelogram, they're the same distance in the same directions. So they're going to be the same vectors. So that's first things first. And then, okay, MP, we can work out what MP is going to be because we can just go from M to N and then N to P. So it's 2A plus 2B. So therefore, M to A is going to be 2/3 of that. So we get 4/3 of A plus B if we simplify that. Using that ratio 2 to 1, we know MA is 2/3 of the way. So, okay, we can use that now to find out what NA is. So NA, we can instead go from N to M and then M to A. So N to M, we're going in opposite direction, so it's minus 2A, and then plus our 4/3 of A plus B. Again, expand, collect together like terms, just so that we've then got explicitly in terms of A and B. We always want to do that. Then now let's try and find N to B. N to B, again, we can work that one out because we've got N to M, which is minus 2A again, M to O, which is 2B, and then O to B is going to be A, because O to P is 2A, and we're told that B is at the midpoint, so it's just going to be half of that. We can put all that together and we get minus A plus 2B, and if we factor out the factor of minus 1, we're basically getting minus A minus 2B in brackets. And now you can see this is end of proof, and I've put the little square again, like in circle theorems. You can do that if you want, don't have to. So you see there, they're both just multiples of this vector A minus 2B. So they are therefore going in the same direction. Therefore, N to A and N to B must be like part of the same line. So that's that. So that's an example of a proof. I'll give you one last example, which is a scenario like this where we've got some quadrilateral and with these vectors. So there's kind of more like complicated vector expressions, but straight away look at that bottom one, AD. Um, we can see that's 2A, so therefore the A is in the horizontal direction. B, we can't really know where B is going, but we know A is horizontal. That may or may not be useful to this question, but I want you to get sort of thinking of it in those terms, try and determine where your A and B vectors are going. So point P is on the line CD, such that C to P and P to D are in the ratio 2 to 1, so kind of usual stuff there. Show that the lines B to C and A to P are parallel. So, okay, let's get our point P in, which is going to be this point here. So, C to P and P to D are in the ratio 2 to 1. So that means C to P is going to be 2/3 of the distance to D. Um, so, what we can then do is we can find out what D to C is. So, you see there's kind of a lot of commonalities regarding these questions. So, we know what fraction of the way P is. It's basically 1/3 of the way from D to C. So if we find out what D to C is, we can then just do 1/3 of that. And D to C we can. Again, we go around the houses. D to A, which is minus 2A. A to B, which is this 2A plus 2B. B to C, which is this 3A plus 3B. We can just use essentially our algebra skills to work all this out, factorize it. It's basically 3 lots of A plus B. So therefore, D to P being 1/3 of that comes out nicely to just A plus B, which is nice. So now what do we need to do? We need to find out what A to P is because we know what B to C is. B to C is 3A plus B. So if we can show that A to P is a multiple of that, a scalar multiple of that, then we've shown that they're parallel. So going a roundabout. So we're going from A to D is 2A. Then from D to P, we've worked out is A plus B, sorry. And finally, if we add that together, we get 3A plus B. And so you see, not only is it, a scalar multiple, it's actually, just 1 times BC. They're actually the same vector. So we've shown, yeah, they are indeed parallel. So that's it in terms of vectors. That's some of the sort of the trickiest problems you can encounter there. A lot of them will be more just simple arithmetic, like what we saw earlier on. But I'm hoping that has made sense. So all we're going to be doing is like addition and subtraction of vectors. You don't have to worry about multiplication of vectors. We don't do anything like that at GCSE. So that's it. That's the end of vectors and the end of geometry. So another big topic, algebra and geometry, 2 really big topics at GCSE level. So did you know vectors can be used to model the motion of objects? So if you're looking to do physics or A-level math, this is something you'll do. You'll be using vectors to model their motions, and this is something that's used in the real world, say in animations, in video games, anything like that, where we want to create the motion of things in a way that is realistic. And the way they do that, they often use actual mathematics and physics equations in those animations, in those video games, in order to to make up things move in a realistic way. And how we do that, like say something like this, if we had a crate on a slant, we would model all the different forces that are acting on this box as vectors. So it's like a force in a particular direction. So first of all, we've got like the weight of the crate pulling straight down towards the earth. We've got this normal force, which is the force of the object pushing back on the crate, pushing it up like this. We've got this force, which is like a net result of uh, the gravity, essentially pulling it, trying to make it slide down the slope. And then we've got this force going backwards, which is the friction, which is trying to resist that motion sliding down the slope. So there's all these different forces going on, magnitudes acting in different directions, and you tally them all up, and to then work out what is the net result that would happen. And maybe it will just stay still. Maybe the frictional force is strong enough for it to just stay still, or maybe not. Maybe it will slide down the slope and fall off. So that's an example of vectors that you'll be using very soon if you're going on to A-level math or physics or anything like that. But if not, there's just a fun fact of how vectors are used in real life. So here you go. Here's the takeaways for today's lesson. Make sure, yeah, you've understood all of that. And next time we're going to be moving on to statistics and then finally probability later on, two closely related subjects that are very different from what we've seen so far. So I will see you then for that.